What's up, guys? Welcome back to Speed, Math, and CS. Today we will be starting our study of AP Calculus AB, which is going to be Unit 1. We're starting off with Unit 1, Limits. So we're going to be doing some experimentation, at least with this course, right? We'll at least for this lesson, we're going to do it mostly in whiteboard. But then, for next lesson, we'll try to see if we can do practice problems in PowerPoint, because I do think we have a super nice PowerPoint here, but we couldn't really do practice problems super easy. So I think we'll stick to whiteboard for now. We don't have anyone in Discord, but we have enough people in Gmeet that I think we'll get started. So okay, let's actually start. So let's start with a simple question, right? What exactly is calculus in the first place? So calculus is essentially the mathematics of, it can be change, and typically I refer to it as infinite math, where you're evaluating things as they approach to infinity. So, for example, things that we do in calculus are calculate velocities, acceleration, tangent lines, slopes, areas, volumes, arc lengths, and a variety of other concepts. And these have enabled scientists, engineers, and economics. If you're taking AP Micro Macro, you know where calculus can be used to solve some stuff. And it helps model real life situations. So as we progress through this course, remember that learning calculus is just one of your goals. Your most important goal is to learn how to use calculus to model and solve problems on the actual AP test. So although pre-calculus mathematics also deals with velocities, acceleration, tangent lines, slopes, and so on, there's a fundamental difference between pre-calculus mathematics and calculus. Pre-calculus mathematics is more static, whereas calculus is more dynamic, right? So for example, in pre-calc, you can only find areas of certain static shapes, certain polygons, rectangles, squares, things like that. But in calculus, we can find areas of all sorts of shapes, regardless of we can find any shape which can be modeled through a graph or some sort. And then, the slope of a line can be analyzed with pre-calc, but in calculus, we'll start analyzing slopes of curves. And the curve of a circle is constant and can be analyzed with pre-calc. But to analyze the variable curvature of a general curve, you need calculus. And same thing, right? Each of the situations involves a similar strategy, right? The reformulation of pre-calc mathematics through the use of a limit as we approach infinity. So one way to answer this question, what is calculus, is to say that calculus is essentially built on limits, right? So the first stage is we take pre-calc, such as the slope of a line or area of a rectangle, and then what we do is we apply the limit process, right? Where essentially we will take a limit as approach to infinity. So this can be infinitely small rectangles to approximate the area under a curve, or this can be infinitely small average tangent lines to approximate the average slope or the instantaneous slope, right? So essentially this cycle, right, throughout this course will be repeated a bunch, right? So without calculus, we can find the value of f of x when x equals c, plug it in. Using differential calculus, we can find the limit of f of x as x approaches c. And then we can evaluate instantaneous slopes, tangent lines to a curve, and the instantaneous velocity, right? And then with integrals, what we can do is normally we can only find area rectangles, work done by constant forces, the center of a rectangle, length of a line of just a straight line. But with integral calculus, we can find the area underneath curves, the work done by a variable force, and the work done by a variable force, the center of a rectangle, the centroid of a region, and the length of an arc, right? So let's start off with the tangent line problem, right? So essentially what we're going to be working through, right, is that in the tangent line problem, you're given a function f and a point P on its graph, and you're asked to find an equation of the tangent line to the graph at point P, as shown. Well, actually, yeah, we could just draw this out. So let's say we have a graph like so, right, with the x and y axis, x and y, like so, right, and then we have a curve like this, and then essentially at this point P, essentially what we're trying to do is we're trying to find a tangent line that's like tangent to this curve at that point. That is our like tangent line problem. And the way we do this is we essentially this was introduced in pre-calc, but essentially we use a difference quotient, right? We will say, hey, okay, f of, in this case we're using P as the point, right? So P plus delta x minus f of P over delta x. So this will essentially be what we use to evaluate it, and later we'll apply limits to this and determine our equation for derivatives. But moving on, the second type of problem we deal with in calculus is finding the area under a curve, right? So in this case, right, we're going to be using limits to get, so it's clear here that the limit that we're using here is like limit as delta x approaches to 0, right? That's how we're going to find the instantaneous slope here. But let's look at our area problem now, where we're trying to find the area underneath the curve. So let's say we have a curve like so, right? And we're trying to find the area. We're trying to find the area in this region, right? Essentially, if you think about it, right, the easiest way to do this is to simply first split it into different areas. So what we will do is let me erase this real quick, but we will essentially split this up into rectangles, right? We'll start with the big ones, like so. So this is a decent job at approximating the area, but in fact, we can get more accurate. And essentially, the way that we will want to do this is, if you think about it, right, we'll have a bunch of like rectangles, right? In this case, let's say the height of this rectangle is using the left point right here, and yeah, for all these rectangles, and then we split the region into 5 rectangles. So let's say we start at 0, and then we go up to like 4, right? Or in this case, sorry. Let's say we go up to 5, right? And we're splitting this into 5 rectangles. Essentially what we'll do, right, is we'll say, okay, hey, let's do f of 0 plus f of 1, so on and so forth, till we get to f of 5, right? And if we're taking bigger rectangles, then we will multiply by the width, right? So we'll have width times this, width times that, right? So on and so forth. But essentially, if we want to evaluate the area under this curve, we're going to need an infinite amount of rectangles. So in this case, we are going to be using a limit to evaluate this, right? Limit as number of rectangles approaches to infinity. So you can see how everything in calculus is tied on limits. So now let's get into how we actually find these limits. So we'll start by doing it numerically and graphically, right? So like have a graphing calculator out for this. And we'll essentially be starting by estimating the limit using a numerical or graphical approach. And then we'll be learning about the different ways that a limit can fail to exist, and also study and use the formal definition of a limit. So an introduction to limits, right? So let's say we have a function like so, right? F of x equals to something like this, right? If we factor this out, right, it's easy to tell this is just x squared plus x plus 1, right? Since if we divide out an x minus 1, that we'll get something like this, right? So, but the thing is, for values other than x equals 1, right? All we have to do is plug into this original equation. But then we can't plug here. Instead we have to plug here to evaluate limits. So essentially, let's say we aren't given this, right? So in this case, we can easily simplify. But let's say we're given something like this, and now we're asked to find the limit. Let's say we're asked to find like f of 1, right? Currently, we don't have the tools to evaluate that, because essentially, if we evaluate 1 under here, right, and do 1 minus 1, that's 0, and we can't divide by 0. So essentially, right, how we're gonna evaluate like a limit, right, is we're gonna use the easiest approach, right? So let's say this is essentially the limit notation, right? X as it approaches to some value, let's say 2, of a function. So this function could be like x squared plus 4, let's say, over x minus 8, right? So typically the easiest and best way to do this is like, if you can plug it in, just plug it in. So in this case, we can simply plug in 2 to our function to determine what the value will be as it approaches to 2. That's essentially what a limit is. It is examining the value as it gets close or approaches x equals 2. So in this case, right, we can simply plug it in, right? We'll say 2 squared plus 4 over 2 minus 8 will be equal to 8 over negative 6, which is negative 4/3, right? So something like that. But let's say we're not able to do that, right? So this is of course the easiest solution. If you can plug it in, you can just plug it in, right? But throughout this lesson, we'll take a look at ways we can evaluate a limit like so. So actually, let's say we're taking the same limit, right? Except now we're tasked with finding the limit as it approaches to 8, right? In this case, we can't just plug it in because we're going to be dividing by 0. So in this case, right, we'll start by using a technique where we'll examine values, and for this we'll need our graphing calculator, right? So we'll start by examining values close to it, right? So we'll say like 7.9, 7.99, and so on and so forth, right? 8, we don't know what 8 could be, right? But then we'll essentially notice as we plug in all of these values, right? 8.1, it'll approach some value, right? And that will essentially be our limit. So in this case, right, if we plug this in, right, this one will be like 15 point, like I think it's like 8 or something. It's like 15.92, and then so on and so forth, right? So it's like 16.08, and then or like 16.2, right? So you'll notice that these values, when we plug them in, they approach 16. And in fact, this is completely right. The limit as we approach to 8 is in fact 16. So our first approach, as you can see, is to simply just plug in values, right? So going back to the thing that we brought up earlier, right? We brought up a graph that looks like this, right? F of x equals to x cubed minus 1 over x minus 1, right? So if we take a look at this graph, right? We said that, so if we graph this out, right? It'll look something similar to this, right? It'll be like 1 here where it intersects, and then it'll look something like this. That's a horrible one, sorry. But yeah, it'll look something like this, right? So let's say that x equals 1 is here. So at this point, we'll have a hole, right? Because we can't really evaluate it here. So essentially what we're trying to do with the limit is we're trying to find a way that we could evaluate that. So the limit method is essentially, hey, what do the values approach from it from the left and right? Because then if they approach some very close value, only at exactly 1 is it a hole. But from other values, we can see what it actually approaches. So essentially we'll do what we did again, right? We'll draw out a table. So we'll say, hey, 0.9, and actually, yeah, I'll draw a proper table this time. So it's gonna be x, there's gonna be f of x, right? So then if we have something like this, right? 0.99, 1, 0.01, and then 1.1. Something like so, right? Then if we plug all of these into our graphing calculator once again, right? We'll notice that for this one, we'll get a value like 2.8. For this one, we'll get like 2.93. And then we don't know what 1 is. But then as we can see, when we plug in such values, we will get things that approach to 3. And in fact, the limit is in fact 3 as we approach to 1 in this graph. So that's essentially how we would evaluate a limit numerically. But one way to do this is another way to do this actually is simply just look at the graph. So graph out a point, graph out like the graph itself, and you can look and see, like, you can do this in your graphing calculator as well. But if you graph this graph, right, and then look at it in your graphing calculator, it will approach some value. So that should also give you a decently good estimate of it'll give you a decently good estimate as to what the value will be. So let's actually get into some more like theoretical like aspect of limits, right? So if you think about something like this, right? And this is just going over how the limits will actually work. Let's say we have a graph like this, like a parabola, right? And then we have a hole here, and then actually the value is down here. Like there's a hole and then the point is actually down here, right? So the thing is, because we're only examining values as it approaches to here, the limit as we approach like this x value, right, will just be the location of this hole. It won't be the location of this. Like this is where it actually is, but we're not going to be looking at the location of this. It's going to be the location of the hole that we're finding, right? So let's say we define like a piecewise function, right? So we have a piecewise function like so. And then let's say we're trying to evaluate the limit as x approaches to 2. So as x approaches to 2 of f of x, right? What is this equal to? So in this case, we'll take the same approach, right? We'll say, okay, well, what do the values get close to as they approach 2 but not equal to? So we'll notice for every value other than 2, it is at 1. So if we're looking at values that are very, very infinitely close to 2, but not equal to 2, we're gonna just get 1. So this limit is in fact just equal to 1. Because remember, for a limit, we're looking at things that are infinitely close, but not exactly equal. Yeah. And then lastly, if we take another graph once again, right? And we have something like this, right? Let's say we have like a break. Something like that, right? And actually this will be a whole knot. But let's say this is an x value and we're trying to find, let's say this is the function of f of x, right? Let's say we are at x equals 2. So let's say we're trying to evaluate the limit as x approaches to 2 of f of x. So in this case, right, once again, we're looking at values that are super, super close to 2, but are not equal to 2. But the problem is, when we try to do that, we get different values on either side. Like on the left side, we'll get values close to, let's assume this is like 5 or something, right? But then on the right side, if we go, we'll get some value in the negatives. So in this case, this is what we call a limit that does not exist. Essentially, we can't find this limit because it approaches 2 different values as it approaches 2. But later today, we'll get into the concept of one-sided limits, where we will only take like limits from the right side or the left side. But for now, if it approaches 2 different values as it gets close to some value, that limit does not exist. So let's move on to the next topic, right? Let's talk about like limits that fail to exist, right? So yeah, limits like so, where they'll break up, like fail to exist. And another one is if we have like unbounded behavior. So if we have something like this, right? And then as it approaches this value, it goes to infinity. And then let's say this is like x equals to 5, right? And we're trying to find the limit as x approaches to 5 of f of x. So in this case, right, because at that point, right, the function just doesn't exist, right? So normally, like if it was a whole, we would be able to find the limit, but the values close to it also are like basically at infinity, like they approach infinity. So in this case, right, it doesn't arbitrarily, remember we defined a limit as so, right? We said a limit, or what am I doing? So we set a limit as x approaches to a of f of a, or f of x, equals to L, right? And that is our limit. But we said that L has to be some constant value. It can't be infinity. Well, at least for now, it can't be infinity. So if the values close to it get to either infinity or negative infinity, or example, we have unbounded behavior like so, then this limit won't exist. So if we have the 2 ways that a limit will like fail to exist is that if we have like unbounded behavior close to that point that reaches to either infinity or negative infinity, that limit doesn't exist. But if we have like a break in the function like we did up here, right? So yeah, so this will be the first case where it doesn't exist, right? Where we have a break in the function at the point we're trying to evaluate. And then this is number 2, where it won't exist. We'll have unbounded behavior and it'll approach to infinity. So, like we said, right? This will be our formal where did I put the formal Yeah, it's right here. This will be our formal definition of a limit, right? The limit as x approaches to a of f of x equals to L. So as f of x becomes arbitrarily close to L, but not exactly L, or as x approaches to a, right? So, of course, in Calc BC, right, we'll be looking at a very rigorous way to solve this, right? We'll use epsilon delta. But in this case, just think about it as the value as it approaches very close to to that limit. So now let's move on to 1.3, right? Where we will instead, because as of now, right, we've simply just been plugging in random values, right, that are get close to it, and then we're assuming that limit exists. So in 1.3, right, we're going to be evaluating these limits analytically, right? So we're going to evaluate a limit using the properties of limit. We're going to use a strategy for finding limits, and we're going to evaluate limits using like dividing out. So for example, dividing out, we already kind of teased this, right? But for this function, we know that we can just divide this out to equal like x squared plus x plus 1. Yeah, plus 1, right? And then now if we plug in this 1 into here, you'll say we get 1 plus 1 plus 1, which equals to 3. So dividing out will be one of our techniques to find them analytically, so we don't have to do all this close like graphing calculator stuff here, right? And then we're going to be evaluating a limit using the rationalizing technique. And we're also going to be introducing something called the squeeze theorem, right? So just to give like a quick teaser as to what the squeeze theorem will be, right? Essentially, we will have two graphs, right? We'll have an f of x like so, and a g of x like so, right? And we're trying to find the limit of some h of x that'll look like this, right? But we know it's in between f of x and g of x. But because of that, this h gets essentially squeezed between the two functions. So as they approach one value, we know that h will approach this value as well, and that'll be its limit, right? So for example, let's say this is like x equals 1. Like I know this is like, in this case, h of x looks very sloppy, right? So we have f of x and g of x, right? So essentially, the limit as x approaches to 1 of f of x equals to 1, and the limit of as x approaches to 1 of g of x, g of x equals to 1 as well, right? So we have two things that approach to 1, and we know that h of x is always going to be less than or equal. It's going to be like between these two functions, right? So in this case, we'll use a squeeze theorem and say, hey, we know it's between these two, and both of these are equal to 1. So essentially, these intersect here. So we know that the limit as x approaches 1 of h of x also has to be 1. So this is a quick teaser as to what we are going to focus on later with the squeeze theorem, but we are going to, of course, do some practice, right, with the squeeze theorem and get to know like how exactly it works. So yeah, so the first thing, right? So in topic 1.2, we discovered that we can simply just substitute in like for example, in our original like limit as x approaches to 1 of f of x, right? We would oftentimes just say, okay, this is just f of 1, right? But like some basic limits, right? If so long as like, or these are like three basic properties, right? If limit as x approaches to c of some constant, right, will just be equal to that constant. And then the limit as x approaches to c of just x itself will be equal to the constant. And then limit as x approaches to c of x to the n is just c to the n, right? So, of course, we can prove this with the epsilon delta, but we don't need to do that in this case, right? All right. So let's go to a strategy for finding limits, right? So we studied several types of functions whose limits can just be evaluated by directly substituting in, right? Let me say like, okay, this limit is just equal to g of 1, right? This limit is just equal to g of 1. But in this case, we're looking at a function that says, hey, the functions that agree at all but 1 point. So let c be a real number, and let's say that f of x equals to g of x for all x not equal to c in the open interval containing c. So if the limit of g of x as x approaches to c exists, then the limit of f of x also exists, right? So essentially, if we're looking back at our function that we defined earlier, right? Limit as x approaches to 1 of x cubed minus 1 over x minus 1. If we're looking at this, right, we'll essentially say, hey, right, in this case, we know that we can divide out x minus 1 from x cubed minus 1. So this will be equal to x squared plus x plus 1. We already know that. And then, so this is using our thing from earlier, right, where essentially x cubed over 1 over x minus 1 equals to x squared plus x plus 1, except for when x is not equal to 1, right? So if x is equal to 1 here, this doesn't exist. But if x equals to 1 here, it is equal to 3. So in this case, if we have f of x where it doesn't agree at one point, and then g of x where it equals f of x for the most part, but it is defined at all points, then we can essentially use g of x, right, plug into g of x to find the limit of f of x. So this is going to be like our dividing out technique to find limits. So yeah, this is our dividing out technique. So let's actually do some practice, right? So our first practice problem, right? Practice problem number 1, let's evaluate the limit as x approaches to -3 of x squared plus x minus 6 over x plus 3, right? So normally if we plug in -3 into the numerator is fine, but if we plug it into the denominator, it's going to be equal to 0. And what we know from this is that the limit as x approaches to -3, if we plug that in, it's going to be, if it's equal to 0, we know it doesn't exist, right? And in fact, we can actually try something. So if we plug in -3 into the numerator, we'll get 9 minus 3 minus 6. So we'll get something like this, 0 over 0, right? So there's going to be a list of values. Like for example, 0 over 0, infinity over infinity, 0 times infinity, and then like stuff like this, right? 0 over 0, like, I don't know why I put an equal sign there, but like values like these, if these ever come up in questions, right? Like 0 over 0, infinity over infinity, 0 times infinity, we don't know what these equal. These can equal any value. But like, for example, let's assume this was like a 3. In this case, 3 over 0, this is equal to infinity, right? So we can say that this limit does not exist, right? If it's 3 over 0, it approaches to infinity. So we can say that the limit either equals infinity or it doesn't exist, right? But let's say it evaluated to like -3 over 0, right? It's going to be the same thing, except it's negative infinity this time instead of regular infinity. So that is how we are going to be defining this function. So now let's move on, right? So yeah, so let's actually get into this problem. So we have an f of x equals to x squared plus x minus 6 over x plus 3, right? So let's try to define a function, right? G of x, right? Because we know that this doesn't exist at x equals -3. So our goal here with the dividing out technique is we're trying to find some g of x that equals to f of x, right? But g of 3 does exist. Or sorry, not g of 3, g of -3 does exist. So for this, what we can do is we can, with the dividing out technique, or like by the dividing out technique, we know that this, we can just divide x plus 3 into this, right? And this, I'll save you the time for factoring it out, but this is just equal to x minus 2. And in this case, g of negative 3 does exist. If we plug in negative 3 here, we get that this simply equals to negative 5. So that will be our limit as x approaches negative 3 of f of x. Because we did what? We found a g of x that equals to f of x, but g of negative 3 does exist, right? So this is, in essence, our dividing out technique. So let's move on to a rationalizing technique. So another way to find a limit, like analytically, or do the same do the same logic where g of x equals to f of x, right? But g of negative 3 does exist at some point. Essentially, what we're gonna do is So essentially, what we're gonna do for this is we're gonna say, hey, right? Another way to find this limit analytically is to simply just rationalize it, right? Where we rationalize either the numerator or the denominator of a fractional expression, right? Recall that rationalizing the numerator or denominator means multiplying the numerator and denominator by the conjugate of either the numerator or denominator, whatever we're trying to simplify, right? So, for instance, if we're looking at a function like so, root x over 4 over x, right? So if we multiply the numerator and denominator by, or actually no, we don't. Yeah, sorry. Let's say we're trying to find the limit as x approaches to 16 of this function, right? So if we look at the top, right, we'll be like, hey, so it'll be 16 in the top, but in the bottom we get over 0. So we don't know that if it exists or not. So we're gonna apply the same thing, except in order to remove this, because this is what's being pesky, right? This root x minus 4. This is equal to 0. So what we're going to do is we're essentially going to multiply it by the conjugate, right? So this will become x multiplied by root x plus 4 over x minus 16. So then essentially if we multiply it out, we'll get some value like that, right? And essentially with this, right, or actually for a better example, right, let's say that this was x minus 16, right? Because then it'll be 0 over 0. Then we actually don't know what it will be, right? So then let's say well, actually, okay, then it's fine. But like it'll look something like this, right? Where we multiply the conjugates. In this case, we still see that if we plug in 16, it'll be 0. So we know it's infinity now. But this is one way, like rationalizing is one way where we can sort of like obtain the answer, right? So if we look at let's try one practice. We'll try a practice problem with this, right? So let's say that we're trying to evaluate the limit as x approaches to 0 . Yeah. So let's say we have something like that, right? So if we directly substitute 0, right, we get 0 over 0. So in this case, we can rewrite this fraction, right, by rationalizing the numerator. So what we will do is we will multiply it by square root of x plus 1, right? So if we do so, we will get a similar g of x, right? Like so. Limit as x approaches to 0 of 1 over square root x plus 1, like so. And in this case, we can evaluate it. Hey, if we plug in 0, it will be 1 over 2. So if you look at that, we just evaluated this limit. And the trick we used here is just simply multiplying by the conjugate. So this is our other way of doing it, right? So lastly, let's cover the squeeze theorem, right? So the squeeze theorem essentially concerns the limit of a function that is squeezed between two other functions, each of which has the same limit at a given x value. So essentially, I teased this earlier, right? But if h of x is greater than or equal to f of x, which is greater than or equal to g of x, for all x in the open interval containing c, except possibly at c itself, and if limit as x approaches to c of h of x equals to L, right? Then the limit of x as approaches to c of f of x exists and is equal to L itself, right? So what we can do here, right? We can actually use this to prove a limit, right? So the first limit we'll try to prove. What? Why did that? I don't know why that happened. Okay, so the first one we'll try to prove is the limit as x approaches to 0 of sine of x over x, right? So in order to do this, let's do like a circular, let's take a circular sector, right? So let's take a circle. Sorry. Yeah. So let's say we have a circular sector like so, and we consider this triangle, right? Sorry, wait. Oh, yeah. Okay, yeah. So sine of x over x, right, is... Oh, okay, I remember now. Sorry. So, remember, we have two sectors, right? The first one is going to be this one right here, right? Second one is going to be this big triangle here. So, essentially, right, sine of x over x is simply this, the area of this sector, just here, sorry, this is very, is going to be essentially a slice of this like sort of circle. Is going to be sine of x over x. And in this case, it's getting squeezed between two triangles, which we know the area of, right? So, in this case, right, we know that the height of this, right, if we just take something like this, right, the height of this is sine x, right? So we know that the area of this triangle is this height times this width, right? And in a unit circle, this is just 1. So the area of this triangle is equal to sine of x. But the area of the, or sorry, because it's a triangle, we have to divide by 2, right? So sine of x divided by 2. But in this case, right, if we're looking at this tall triangle over here, right? This one is equal to this height is equal to tan of theta, right? Because if we're using opposite over adjacent, right? Opposite over adjacent, right, is equal to tan theta, right? And we know that this is 1. So we know that this has to be tan of x, right? And once again, it's triangle, we divide by 2. So essentially, we know we are essentially squeezing sine of x over x between sine of x over 2 and tan of x over 2. So if we want to find the limit as x approaches 0, let's plug in 0 to both these functions, right? Sine of x, if we plug in 0, right? Sine of 0 is equal to 0. 0 over 2 is just 0, right? Tan Or sorry. We actually have to manipulate more stuff first, right? So right now we know it's sine of x is x, right? So we have sine of x over 2 tan x over 2, right? And essentially, this is going to be our squeeze, right? So if we multiply each of these expressions, I won't actually do this right here, but if we multiply each expression by 2 over sine x, right? This one's what? This one's going to become 1, right? 2 over sine x. This will become 2 over x, right? Greater than or equal to cosine of x. Cosine of x. Like so, right? And then by this, if we plug in x is equal to 0, right? This one still doesn't exist, right? Sorry. So then if we plug in 1 for both of these, right, we'll see that both are equal to 1, right? And this will essentially get squeezed at 1. So we know that sine of x over x is now 1. So we can do the same thing, and we'll have more practice on this. But that's essentially how our squeeze theorem is going to work. So we're almost done here, right? But we have to let's quickly talk about how continuity at a point works, right? So essentially, continuity at a point, right? So this is continuity. So we're almost done here. We have 10 minutes left to work. Continuity, keep spelling that wrong, right? So continuity, we have 3 rules, right? 1, 2, 3. Continuity at a point, right? The function f is continuous at c when the following 3 conditions are met, right? First condition, f of c exists. Second, the limit as x approaches to c of f of x also exists. And then lastly, the limit as x approaches to c of f of x equals to f of c. So something like so, right? So these are our 3 rules for continuity. So that is essentially how our continuity will work. And next, let's look at one-sided limits. So one-sided limits are pretty simple. Essentially, we are just going to examine values from one side of the limit, right? So we'll say if the limit of x approaches to 2, right? If we're going from the right, we're going to put a minus above the 2, or going from the left, sorry. So this tells us to examine values such as 1.9, 1.99, and so, right? And then if, for the other one-sided limit, x approaches to 2 from the positive side, we're going to be looking at values such as 2.1, 2.01, so on and so forth, right? So this is essentially the type of values we're going to be looking at. So yeah. And then the properties of continuity, right? If we have a function b, f, and g are continuous at c, right? If we multiply f by some constant, it's going to stay continuous, right? F plus g, f minus g are going to also be continuous. F multiplied by g is also continuous, and f over g is also continuous so long as g over c is not equal to 0. So properties of continuity, there are 4. So they'll be like so, right? So the scalar multiple, right? So if we have b times f, right? In this case, we're assuming f and g are continuous, right? If we multiply this by any scalar multiple, it'll still be continuous, right? Sum or difference, f plus or minus g is continuous. F multiplied by g is also continuous, and f over g is also continuous so long as g of c is not equal to 0. Of course, there's a proof for this function, which we might cover like later down the line. But essentially, that is our proof of so. So now let's look at our which will probably be our last topic for today, right? Let's look at IVT, intermediate value theorem. So if f is continuous on the closed interval AB, f of A is not equal to f of B, and K is any number between f of A and f of B, there must be one number C in A to B such that f of C equals K, right? So this is like an existence theorem, which essentially says, hey, right? We have a graph like so. Let's say we're at point A here and point B here, right? We take these 2 points and we examine the area around them, right? And then we choose some value in between f of A. So f of A will be like here, and f of B will be like here. So if we choose any value in between them, right, it will touch the graph at some point, right? And we can see right here that this is most definitely true. So this is essentially what IVT is saying. And the thing being an existence theorem essentially says that, hey, we are only going to tell you that it exists, not where you can find it. So yeah, I think. Oh yeah, we did talk about vertical asymptotes, right? So vertical and horizontal asymptotes, right? So for vertical asymptotes, right? If we notice that the limit as x approaches some value of c of f of x equals to infinity equals to plus minus infinity, then it is a vertical asymptote. And then to evaluate horizontal asymptotes of the function, well, we'll have to evaluate the limit as x approaches to infinity of f of x, right? Whatever that equals will be our horizontal asymptote. And as x approaches to negative infinity of f of x, it'll be some value, right? So if both of these are either, there's two cases. If both of these are either equal to plus minus infinity, right? If both these are either equal to either positive infinity or negative infinity, then this is just a normal function, meaning that there's no horizontal asymptote. But if this approaches some value, we know there must be a horizontal asymptote. So yeah, that will be it for today. But before I go, I just want to real quick do some practice, because squeeze theorem is important, but I want to do a little practice for squeeze theorem, right? So this will be the last thing we do before we go today, right? So we practice problem number 5, right? So let's say we're trying to find the limit as x approaches to 0 of x multiplied by cosine 1 over x, right? Essentially, what we'll do here is we'll look at the bounds, and we'll try to define two functions, right? In this case, because we have a trigonometric, so this x, right, we'll say it ranges from negative infinity all the way to positive infinity. So we can't squeeze x between two graphs, right? But a trigonometric function, we know that this will only ever return a value. And yeah, just so you know, if you normally plug this in, you'll get cosine of 0 times cosine of infinity, right? You don't know what cosine of infinity is, so you just straight up don't know what that value is if you try to plug in 0. So plugging in by substitution won't work, right? We know that all trigonometric functions are squeezed between -1 and +1. So if we look at this and try to evaluate this, right? We know that it has to be greater than or equal to x multiplied by -1, right? Or negative x. And we know that it has to be less than or equal to x multiplied by 1, which is just x, right? So we know that x times cosine of 1 over x right, falls in between these two functions. And would you look at that? If we evaluate the limit as x approaches to 0, both negative x and x approach 0. So we can say that the function in between also approaches 0. So this limit right here, which we aren't able to evaluate, we can now evaluate this as equal to 0. So if we think about it, right, let's actually generalize this result. So the trick is, every time you see a function like so, right, with like cosine, tangent, you always want to look at the different factors and see which one can be bounded. In this case, x can go without bound, but we notice that all trigonometric functions have a bound of -1 to 1. So we can squeeze it in between those two functions in order to evaluate limits. So that is a strategy for squeeze theorem. And of course, there will be tons of practice for squeeze theorem on the homework. But so there's going to be tons of practice on the homework itself. So no need to sweat if this doesn't make sense. And also make sure to check out the homeworks at homework-speed-math-cs.glitch.me. It'll be the top link in the description. But we hope to see you in the next one. Yeah, bye.